So I'm Pat Clemins. I manage the cyber infrastructure and partnerships for Vermont EPSCoR at the University of Vermont. I have a research appointment over there in computer science as well for researchy kind of things. And over the last 7 years, we've built an integrated assessment model with Pegasus. And so they asked me to talk about that. Before I begin, as the kind of the first user, I wanted to really thank Pegasus and the ISI team for putting this conference together. I'm super excited to see other people are using it. And I know people are doing a better job using it than I am. So I'm really excited to learn how people are doing it right. And me going first does not imply any kind of expertise or the fact we're doing it well. I just do the short straw. So I want to talk a tad about the research, but then I want to quickly get into the Pegasus computing stuff, because I think that's the most interesting for this crowd. But to give you a broader sense of what we're doing, integrated assessment modeling has been kind of the core of our research over the past 2 grant cycles. Our current project is called Basin Resilience to Extreme Events, or BRE, and that focuses on understanding how extreme climatic events and human-induced events affect harmful cyanobacteria blooms in 2 shallow bays of Lake Champlain. And you see one of the bays there in the model output from one of our bays on the right there, and that's temperature. You can kind of see the cold water coming in from the southeast corner from the main river input, and then it swirls around and does fun stuff. And we use that to kind of see how the system's operating. And so we started this modeling actually 1 grant cycle ago with something we called RAC, Regional Adaptation to Climate Change. And we found that it's the extreme events for any given year could produce up to 50% of the nutrient load into the lake. So that's how we got from kind of climate change to extreme events. We saw that they had using Pegasus and this integrated assessment model, that extreme events had a kind of overwhelming effect on the lake. And so we've focused on that for this last 5 years. So integrated assessment models project the impact of policy scenarios on socio-environmental systems, and they're providing policymakers with data to make informed policy decisions. So in our case, our SES is a Lake Champlain basin. And some of the policy scenarios that we've explored thus far are variability in climate change projections, land use change, agricultural best practice adoption, and then the efficacy of those best practices. So what does the model look like from an overall view? So we have implemented all of these different models separately. Each kind of modeling team in each domain has calibrated and kind of published on these models separately. And then the IAM team, which I have the technical lead on, integrates all of these into this IAM. So we have a team of climate modelers that downscale climate to the region so that we can operate on a 1 kilometer range, because Vermont's small, the basin's small, and global climate models don't really do it for us. We need a smaller resolution. We have a land use model, and that projects going forward how land use might change using an agent-based modeling system. We model each landowner as an individual agent, and based on inputs of climate, economy, policy changes, the land use might change. So we might have a larger urban footprint, or farmers might choose to cut down some trees and convert farm to agriculture, or vice versa, let lands go fallow and trees grow back. So that's our land use change model. And we have a watershed model that tells us how the water falls from the sky, hits the mountains and the different kinds of land use, and flows through the rivers and streams and ends up in the lake, including biogeochemistry as part of that. And then we have a lake model that takes the inputs from the rivers and streams, tells us how the water spins around in the lake and how the nutrients mix, and then the possible probability of cyanobacteria blooms. We also have 2 modeling groups, governance and microeconomic, that have kind of informed our boundary conditions for the model, but they aren't currently integrated in the IAM. So one other thing I want to point out is that there's a lot of arrows on this diagram. So a lot of feedbacks, feed-forwards, and so that was one of the challenges we had with Pegasus that I'll get into, and how we got around that. So some of our computational challenges that led us to Pegasus. It was clear early on that we wanted to use best-in-class community models for each IAM domain. And that means that each model had different platform requirements. So most IAMs you'll encounter are basically one EXE. They take all of the modeling best practices that they want to use from each individual model, compile it, and run an IAM in like one or two EXEs. We did not choose to go that route because we wanted to use these best-in-class models. But that also meant that we have models written in Java for the land use. We have our watershed model in C++. We have our lake model in Fortran, which is actually a Windows binary. So we have to figure out how to run some stuff on Windows or using Wine. And so we had all these different platform requirements, and Pegasus handled that really well. And so that's kind of one thing that pushed us there. We had these feedback loops. And again, I'll get into that, how we took basically a directed, we kind of used DAX in a cascading kind of format to get around the idea that we wanted to not just feed forward down the pipe, but also feedback over time. In any kind of big modeling project like this, you have to orchestrate data flows between the models. Again, Pegasus does that really well with Condor on the back end. Like I said, we run multiple scenarios with each run. So the install manager would have been really nice for this, but we didn't have that at the time. So we kind of built our own kind of ensemble manager, and we managed execution of multiple scenarios in parallel, actually up to 176 at a time. And then we found out that when we run these multiple scenarios, they quickly outgrow the computational resources of our workstations here. And so to give you a sense of like our big workflow, we've run at most 176 scenarios in one workflow at a time over 60 years, which consumes about 10 days of all time, equals about 6.5 years of CPU time, 25,000 jobs, and generated almost 3.5 terabytes of data. So one workflow isn't that big on its own, but once you start multiplying it over years to project to the future and multiple scenarios, it gets big really quick. So these are the things that led us to Pegasus. So let me go through two things quickly that I think that we did that were kind of unique in how we use Pegasus, and hopefully these are of interest to the group. So the first thing we had to solve was how to do feed forward and feedbacks within that big IAM diagram that I showed you originally. So what we did is we arranged our model sequence, our workflow sequence, into what we call cascades. And we run each cascade for a decade. So the way that we designed this was very intentional. We have slower moving models that aren't as affected quickly over time at the front, at the top of the cascade, and then models that are more reactive to things in a quicker time scale at the bottom. So things like land use change very slowly. So land use gets put at the top of the cascade. And as you move down the cascade, every model further down the cascade has access to the current run, the current 10 years of data from any model above it. So RESIS can have the 10 years and most recent history of the all AVM as it runs, and then which is a hydrology model, and then the two pieces of the lake model below that, EFDC and RCA, then have access to the hydrology model basically in real time. And we do this for every 10 years. And then the next 10 years, we repeat this whole schedule. So now the all ABM has, as it projects forward for the next 10 years, access to the last 10 years of lake data and hydrology data as it goes forward. So we basically do this in kind of a large loop. And we picked 10 years as kind of arbitrary, but we could do this for any amount of time. And there is some spin up involved with the models, so we didn't want to do this too often, because like RESIS has to have 2 years of spin up every time. The lake model needs 3 years. So to reduce like these computational costs of spin up and things like that, we kind of settled on 10 years as the best time frame for these cascades as we move to the future. So I hope I explained that in some way that makes sense. So the cascades provide those feedbacks, and then internally within the cascade, we are able to do the feed forwards. And this diagram also shows how we run all these scenarios in parallel. So this just shows 4, and like I said, we've done up to 176 at a time. So UEM is not a research one university. We have an HPC, but we don't really have a lot of HTC, which is what we really need for Pegasus. So what we did is we went out and got an allocation on UCAR's Yellowstone and Cheyenne HPCs, and then wrote an interface for it. So when we started this 7 years ago, there was no Bosco, High Glidin, G-Lite. We had Glidin, but the scheduling with trying to get it to run on the remote system at the right time for the right amount of time and then fill it up was quite an orchestration challenge. And so we found it easier to just kind of write our own UCAR access server. And what we do is use SSH to submit via PBS all of our jobs. And we're able to bundle those in bundles that make most efficient use of the nodes. So we know that the nodes have 36 processors. So we take jobs that have, we accumulate jobs that use all 36 processors and ship it over in one bundle via. And then we use QStat to constantly monitor how those jobs are doing on the UCAR system. And then we use Globus for all the file transfers because file transfer over SSH is ridiculously slow. So between Globus for file transfer and SSH for the submission and the status updates, we're able to take these UCAR workers, which bundle all of the local jobs into kind of node-friendly execution packages, send it to the UCAR server, which sends it over to UCAR, and then feeds it back. And then we also have local workers running. So some of our jobs run locally. And so you see in that diagram on the left, we have Pegasus submitting local workers for our own HTC Condor cluster on our campus. And then we send jobs that are better suited for the node-based HPC environment through these UCAR workers. And so if we did this today, we'd probably use something very different. But 7 years ago, this was kind of the best we thought we could do. So this feedback session. So I don't know if I did this right, and I hope this doesn't set the stage for what everyone else is doing. But my feedback is I wanted to keep it very high level. I didn't want to start individual bug reports. I kind of wanted to take a step back and look at the 7 years and see what was really helpful with Pegasus for us. So the first thing is I'm really glad that Eva's LIGO presentation he talked about originally went the way it did, because for us, Pegasus is most effective because it's a computational tool for computational scientists and not some GUI web interface. I feel like we have a lot of workflow managers out there like Kepler and Galaxy that are web-based and GUI and really easy to use for all of my non-computationally expertise of users. But we have a small core of people that know how to use computing and can write code effectively. And for us, that's where Pegasus is really important, and I think holds a unique spot in the market. I mean, as I thought about this, the only other really workflow manager like Pegasus is Apache Airflow, which I saw someone mention on Slack. And so the idea that Pegasus isn't necessarily user-friendly, like I can't give Pegasus to my, to some of my non-computationally experienced researchers to use. But for us and our computing team, it has been exceptionally helpful. And so my first point is trying to get at that I hope that Pegasus continues to focus on its audience that it has in the past and not turn into like a GUI interface that's easy for everyone else to use, because there's the strength of those computational tools are really important for us. Having said that, the Pegasus service dashboard has been really slick. I can spin it up, give that web page to my users, and they can monitor the jobs as they go. So that's been our experience with Pegasus that way. The second point is maybe out of date, but it's been over the 7 years kind of the biggest pain point for us in Pegasus, and that's access to HPC clusters. So, like I said in that previous slide, we kind of wrote our own HPC access server. And when I originally wrote this, I said, wouldn't it be great if Pegasus had like a built-in PBS batch manager that collected jobs at similar runtimes for us dynamically as the workflow executed, and then it could package those together and submit them to make maximum use of nodes, and maybe include Globus file transfer support. And then I said, you know what, I don't know if that's the greatest thing to do anymore. You know, with OSG, we can just plug OSG into the back end and have access to tens of thousands of OSG nodes. So maybe that's actually the future. And this HPC cluster thing is kind of a legacy thing of the past. It would have been really important for us a couple of years ago, but now as things change and move, I'm not quite sure this is the direction that we should be going. So I say this in the sense that, you know, I wish we would have had it, but now I'm not sure that I wish we have it anymore. So that's kind of where that point comes from. And then the last point is that I feel like post-analysis, workflow analysis and troubleshooting is still too difficult. When something fails, I have to dig too far into the data directory of the workflow to find out why. And sometimes my system out and error gets cut off within the peg system out errors, and I wonder why the HE Condor out and error just aren't saved in their raw, and I can do a tail on it and find out, you know, what the exception was at the end that made that job crash. And sometimes jobs just hang. I don't really know why. So if there was one improvement I think that I could make in Pegasus today is that the post workflow analysis and troubleshooting of why jobs fail would just be a little bit easier. And again, so I also say that a lot of this might be the fact that I don't know what I'm doing, and maybe I need some training. but these have been the pain points for us as we've used Pegasus over the last 7 years. So with that, I thank you for your attention.